Hey class, welcome back. We're going to wrap up chapter 10 today, chemical bonding, and we're going to pick up exactly where we left off, where we were investigating the concept of polar bonds, and we know that we can classify a bond as polar, right, if the electronegativity between a bond between two elements, so between element A and element B, all right, this covalent bond right here, and this bond is considered polar if the electronegativity difference is anywhere between 0.5 and 2.0 on the electronegativity difference between A and B. So if it's anywhere between 0.5 and 2.0, then we can consider this bond a polar covalent bond. Anything less than 0.5 is considered non-polar covalent bond, so there's an equal sharing of electron density. And anything above 2.0, we're going to go ahead and say that the electronegativity difference between A and B is so great that this actually isn't a covalent bond. It's going to be an ionic bond because the electron is transferred from the least electronegative atom to the more electronegative atom. So now that we can understand and classify bonds as polar or nonpolar, how does that affect the polarity of the molecule as a whole? So does the presence of one or more polar bonds in a molecule always result in a polar molecule? And the answer is no. Well, first of all, let me take a step back. Polar bonds, right? If a molecule is made up of polar bonds, odds are the molecule is polar. But there are some exceptions where that is not the case. So let's first talk about what it means to be a polar molecule. A polar molecule is one with polar bonds that add together. They do not cancel each other out, and they form a net dipole moment. So basically, just like what we talked about with water, those two bonds in water between OH, right? These two bonds are considered polar. And collectively, when we look at the fact that these two bonds are polar and we look at the shape of the molecule as a whole, we know that the molecule as a whole is polar as well, meaning that there's an unequal distribution of electron density within the molecule. This side is more electropositive. This side is more electronegative, right? And the molecule as a whole has a net dipole moment. So a polar molecule like polar bonds has a net dipole moment, a collective amount of dipoles that don't cancel each other out. If a diatomic molecule contains a polar bond, right, then the molecule is also considered polar. For molecules with more than two atoms, it is more difficult to tell whether or not the molecule is polar from nonpolar ones because two or more polar bonds may cancel each other out. So what this essentially saying is, okay, two things. Most of the time, polar bonds lead to polar molecules. And in order for a molecule to be polar, it has to have a net dipole moment. Okay, so that's the first thing. The second thing is diatomic molecules are really, really easy to classify as polar or nonpolar. All you have to do, right, is just look at one bond. If that bond, such as HBr, if that bond is polar, then the molecule itself is going to be polar. Okay? But with molecules with more than two atoms, all right, this is anything else besides diatomics. For molecules with more than two atoms, it's more difficult to tell polar molecules from nonpolar ones because two or more polar bonds may cancel each other out. So basically what that's saying is it really, even though a molecule might have polar bonds or be made up of all polar bonds, it might not be polar because we always have to consider the shape of the molecule. If the molecule is shaped in such a way where the polar bonds cancel each other out, then the molecule itself will be nonpolar. So for example, let's look at carbon dioxide. Okay, carbon dioxide is a perfect example of this. If we look at carbon dioxide, okay, and if we just evaluate the bonds, so to speak, carbon has let me just go double check really fast. Oops, excuse me. Carbon has a electronegativity of 2.5, and oxygen has an electronegativity of 2.5 and 3.5. So that's greater than 0.5, right? The electronegativity difference is 1. So that means that this bond is polar, and so is this. Okay? So if I were to ask you, is carbon dioxide a polar molecule? A lot of you might sit back and say, well, yeah, because it's made up of polar bonds. If the bonds are polar, then the molecule has to be polar. But that is actually not true. Turns out, even though carbon dioxide is made up of polar bonds, it is collectively not polar. Or we'll say it is a non-polar molecule. And then you might ask yourself, or ask me, well, how is that even possible? And that's because even though carbon dioxide is made up of polar bonds, it has a linear geometry. All right? The dipole moment of one bond completely cancels out the dipole moment of the other, and the molecule is collectively, or has no net dipole, so it is nonpolar. So sometimes, and a lot of times when we represent polar bonds in chemistry, we represent them with this arrow right here, where we start off, we draw it like this, okay? And we draw it towards the electron density. So E density is where the arrow points to, okay? And another way that I like to think of it is that this end of the arrow looks like a plus charge. Okay, so we start off where the plus charge is, or the pseudo plus charge, right, or the least electronegative atom, and then we draw an arrow towards the more electronegative atom. These are called vectors, okay? And essentially what we're looking at is that if two vectors are pointed in equal and opposite directions, right, when we add them together, the vectors cancel each other out. All right. So if we represent bonds, polar bonds, as vectors, and if we look at CO2, for example, right, if we represent these polar bonds as vectors, you can see here that if we were to add these two vectors together, they would essentially cancel each other out because they are pointing in equal, or in the opposite directions, and it's equal. Okay, so they're pointing in equal and opposite directions, so essentially they're canceling each other out. Another way that you can look at it is since the electron density is being pushed this way in this direction, or in this direction, and being pushed this way, right? There's no unequal distribution of electron density within the molecule, right? If this oxygen here has more electron density on this side, or that amount of electron density on this side. This oxygen has a certain amount of electron density on this side, and collectively, if we look at the molecule as a whole, there's no unequal distribution of electron density. All right, this oxygen is pulling electron density in an equal and opposite direction as this one. So there is no unequal distribution of electron density within this molecule. So even though it's made up of polar bonds, it is collectively nonpolar because there is no net dipole within the molecule. And that all has to do with the fact that CO2 is linear. Okay? So again, this is just going back to the vector notation. We can represent polar bonds with arrows, these are called vectors, that point in the direction of the negative pole and have a plus sign at the positive pole. just as I showed you for carbon dioxide. If the arrows point in exactly opposite directions, and if they point in exactly opposing directions as they did in carbon dioxide, the dipole moment cancels, okay? In the vector representation of a dipole moment, the vector points in the direction of the atom with the partial negative charge. And again, that's going towards the more electronegative atom. But again, if these vectors point in exactly opposing directions, as they did with carbon dioxide, the dipole moment cancels. And the molecule is non-polar. So let's look at water, for example. Water is another molecule that's made up of polar bonds, just like what we said. Okay, each bond is polar here, and this is exactly what I was talking about earlier, here and here. And if we were to draw the polar or represent the polarity of the bond using vectors, right? We would draw a plus sign here, draw an arrow, plus sign here, and draw an arrow. Okay, and what that's doing is and you can see here that the purple arrow is the summation of the two vectors, okay? The summation of the two vectors shows a net dipole change. This is all because water is bent. So it has an unequal distribution of electron density. The electron density is up here, or up here, and there's a lack of electron density down here, here, and here, right? The shape of water, that with the fact that it's made up of polar bonds, makes the water molecule polar, okay? The fact that CO2 is linear, even though it's made up of polar bonds, CO2 is nonpolar because it's linear. So another way that you can look at it, it's saying the same thing over and over again. Water has two dipole moments that do not cancel, and therefore the molecule is polar. So here's a really good representation, a really nice slide. I always had a hard time, honestly, with at the beginning with polarity, collective polarity, right? Net dipoles and molecules. And how do I know if vectors cancel each other out? So these are common cases, okay? So the first one, two identical polar bonds in opposite directions. This is a linear molecule. The molecule is nonpolar. If we have a trigonal planar, geometry made up of polar bonds, such as this one right here. So even though it's made up of polar bonds, if these bonds are all equal in polarity, the molecule, if we were to add up these vectors, basically what we're looking at, the fact is that this entire molecule as a whole does not have unequal distribution of electron density because we have a bond that's polar here, bond that's polar here, here, and here. And as you can see, just from this representation of how I drew it, this bond is nonpolar, or this molecule is nonpolar because it's uniform. The electron density is uniform around the molecule, all right? It's the same amount of electron density up here as it is down here, as it is down here. So the three identical polar bonds at 120 degrees from each other will cancel. The molecule is nonpolar. If we have some type of bent situation, this is trigonal pyramidal, such as NH3, right? NH3 is trigonal pyramidal, ammonia, made up of polar bonds. Three polar bonds in a trigonal pyramidal arrangement will not cancel, and then the molecule is now polar. Bent arrangements, all right, two polar bonds with an angle of less than 180 degrees between them will not cancel, the molecule is polar. And then finally, 4 identical polar bonds in a tetrahedral arrangement, 109.5 degrees away from each other. The dipoles will cancel, the vectors will cancel. The molecule is nonpolar. Okay, so the key for this, the key take-home message is that not only is it the polarity of the individual bonds that make up the molecule, but it's also the shape of the molecule too. You have to take both of those into consideration, all right? Now, of course, if you have a molecule that's made up of nonpolar bonds, regardless of the shape, that molecule will also be nonpolar. It's when the molecule is made up of polar bonds, do we have to evaluate the shape of the molecule, and then once we evaluate the shape, we can sit back and say, is the molecule, or ask ourselves, is the molecule polar or not? So again, trigonal planar, most of the time, trigonal planar molecules, right? If all of the bonds are identical, those guys will be nonpolar. The same with linear arrangements. Trigonal pyramidal, if it's made up of nonpolar bonds, will be nonpolar. I'm sorry, if it's made up of polar bonds, it will be polar. Bent arrangements, if it's made up of polar bonds, will be polar. And then trigonal planar, tetrahedral arrangements, if all of these bonds are identical, right, like carbon tetrachloride, even though this is made up of nonpolar bonds, polar bonds, it has a tetrahedral shape. So the dipoles will cancel each other out, and the molecule is collectively nonpolar. Okay, so this is another, again, this is just the same thing that I've been saying. These are all the electronegativities given for the periodic table. And again, if we're looking at a difference of, I said 0.4, but it's really, it's 0.5. If it's greater than 0.5, we have an electronegative or a polar bond. Okay, and these are examples that we can go over again. We know H2O is polar. We know NH3 is polar, but when we discuss, we can evaluate these in our lecture class. So I'm actually going to keep skipping because these are kind of just, so if you have so BF3, we never really talked about BF3, but we know that fluorine is the most electronegative atom. So anything that fluorine binds to is, if it's not an ionic compound, if it's a covalent bond, it's going to be polar because fluorine is so electronegative. So BF3 is a really good example, another really good example of a molecule that's made up of polar bonds, but it's collectively nonpolar, all right? So it's, again, due to the shape, all right? This is the shape, this is trigonal planar. And what this picture is asking you to think about is, like, if you want to put boron in the center and think about fluorine as these 3 people, okay? I would have it be like maybe 3. I would have done it a little bit differently and said these 3 people were like triplets. So essentially they're all the same. Not essentially, they are pretty much the same. Genetically speaking. So what you can sit back and say is that if we have 3 people pulling in equal and opposite directions from boron, as if fluorine is pulling electron density away from boron, right? What will happen is these guys are pulling in equal and opposite directions, and ultimately what will happen is there's no net change, okay? Nobody's going to be pulling any stronger. There's not going to be any uneven distribution of this rope anywhere along this line, okay? So again, shape has a lot to do with whether or not a molecule is polar. And then finally, I'm just going to wrap it up here really quickly. So polar molecules, you're going to hear this a lot in chemistry. Like dissolves like. I'm going to write that down. Like dissolves like. And what we mean by like, similar polarities dissolve other similar polarities. So if you have two substances and you put them together, one is nonpolar, the other is polar. So for example, oil is nonpolar, water is polar, and since these substances have a difference in polarity, they do not mix, okay? So things that have similar polarities do mix. All right, so water, that's why water dissolves ionic compounds. That's why we can mix water and ethanol together. Anything that's miscible or mixes in with water, that's because that substance has a similar polarity that, as water does. Water will not dissolve anything that's nonpolar. Okay, so polar molecules attract each other. Dipole-dipole interactions, hydrogen bonds, we haven't talked about that, but we will a little bit later. Also, polar molecules make up for high boiling points and melting points, and they also mix well with other polar molecules. Again, they don't mix well with nonpolar molecules. This is an example of oil and water. Nonpolar molecules, however, don't attract other molecules at all as well. They have London dispersion forces. This is an intermolecular interaction that we'll talk about later on. They also have low boiling points, but they do mix well with other nonpolar molecules. And again, this goes back to the like dissolves like situation. So the take-home messages from this slide, right, is that we don't know, I haven't introduced dipole-dipole interactions to you or London dispersion forces yet, so let's kind of ignore those. Polar molecules attract each other, they dissolve well, they mix well with each other, they mix well with other polar molecules, and they also tend to have high boiling points and melting points, okay? Non-polar molecules don't have a lot of attraction forces associated with them, okay? They have which results in low boiling points, but they do mix well with other nonpolar molecules, okay? Oil will mix well with other oils. Oil mixes well with butter, all that kind of good stuff, okay? So the polarity of a molecule directly determines how well it interacts with other molecules and how certain physical properties such as boiling point and melting point. Okay, and with that, we're going to actually stop chapter 10 and we'll pick up with acids and bases right after this.